These are the notes for day 25, which is called the fundamental theorem of calculus. So I'm going to start with the bottom part here. What's happening down here is they're just going through a comparison between the two branches of calculus that we know so far. Division is an inverse operation of multiplication. Division is kind of like finding the change in y over the change in x. So the slope of a line, which is change in y over change in x in pre-calc, would be connecting 2 points and finding the average rate of change. In calculus, we know that the slope of the tangent line is the first derivative. If we take this derivative statement and do the inverse operation, which is multiplication, we can find the area of a rectangle by doing base times height. Or in calculus, we could find the area under a curve by taking the limit process and doing lots of bases times heights to get the exact area under the curve using a limit process. So the overall fundamental theorem of calculus states this. If you take the antiderivative of a function between two values, and this is now called a definite integral because we have a definite starting point and an ending point, after you find the antiderivative function, so f of x changes into a new function labeled capital F of x, and then if I plug in the endpoints, b minus a, this quantity here represents the area under that f function between a and b. All right, this is a little bit of a dirty trick, but there's actually 3 examples on this page and not just 2. First one says use the graph to determine whether that area is positive, negative, or 0. So if I'm going to go from -2 to 2, from -2 to 2 on this plot, and if I find the antiderivative of that, I want to know whether or not the final quantity is positive, negative, or 0. And the way we estimate that is we shade areas. So from -2 to 2, area under the curve is positive here and negative over here. And either by inspection or by estimating, by counting some boxes, we can see that this negative area is probably going to be larger than this positive area. So our overall answer is negative. I don't think those 2 areas are going to cancel out. I think that the negative area on the left is greater than the positive area on the right. And again, the reason why this area over here is negative is because we're calculating the area under a curve up to the x-axis. So if your function is negative, getting up to the x-axis represents a negative area, whereas if your function is positive, the area underneath that function to the x-axis represents a positive area. All right, before we do the example that's typed on in your notes, I thought it'd be better to throw in a more straightforward example to look at first. So what's happening here is I want to find the area under this parabola between 2 and 5. So pause the video, calculate the antiderivative, and then look at the fundamental theorem of calculus and see if you can figure out the final answer. We need the antiderivative first, which you know how to do, and then we're going to substitute 5 and 2 into that antiderivative. Pause the video and see if you can come up with the final answer. Okay, so here's the process. The antiderivative is this, and then at the end, what I have is a statement that says I want to evaluate this function between 2 and 5. So substituting in 5 to the cubic function, and then subtracting off 2 substituted to the cubic function. And it's very important that you remember these parentheses because you want to subtract off all parts of the second half of the statement. So again, the fundamental theorem of calculus says capital F of B minus capital F of A. So continuing on with just some calculations, we get 78. Now it says use a calculator to verify. So what you're going to do now is put the function into y1, and you don't have to do it this way, but this is just getting you into good habits for future. Put the function into y1, press the math button, and then option 9 is FNINT. That stands for function integrate. Okay, you need to tell your calculator what function you want the antiderivative for. We want what's written in y1. You need to tell it what variable to take the antiderivative with respect to. So that's kind of like the dx statement. So this is always going to be x in your calculator. And then you need to give your calculator a starting and ending point. So we're going to start at 2 and end at 5. If you typed it in correctly, you wind up with 78. y1, again, as a reminder, is inside vars, y vars, choice 1. There. Okay, so now for the more complicated one, this one. I need to find the area under that rational function between -2 and 1. So my hint or my suggestion is take that rational function and separate it into 2 simplify, and then find the antiderivative. And again, pause the video and see if you can figure out the final answer. Okay, here comes the answer. Simplifying, we get u and u to the negative 2, separating the two different antiderivative statements, keeping the same definite limits, negative 2 to 1. Antiderivative of the first is 1/2 u squared. Antiderivative of the second is negative u to the negative 1. Remember your power rule for antiderivatives. I'm going to subtract these two functions because the original question had a subtraction sign inside there. Substituting, simplifying, and this. Go slow through the substituting and simplifying step. There's lots of different subtractions and it's very common to make silly mistakes. Okay, so when I go to check on my calculator, I get nothing. My calculator stalled out. It would not produce an answer. And that's because this is a little bit of a bogus question. We should not be doing the antiderivative there. Why not? The issue is that this function is not continuous and differentiable on the interval negative 2 to 1, okay? If you look at this function, x, or u, actually, u cannot equal 0. And since 0 is between negative 2 and 1, we cannot use the fundamental theorem of calculus on this problem. When you try this on your calculator, it will sit and spin for a fair amount of time, and then it will give you some sort of an error message. My error message said tolerance not met. That means that its numerical analysis couldn't figure out the example because we pretty much asked us a bogus question. The dangerous part here is that you can crank through all these calculations and come up with a numerical answer. It's just not correct. So you really need to pay attention to domains, and you need to make sure that your function is continuous and differentiable on the interval that you're inspecting. Okay, these final two examples are just special cases that I thought I'd walk through so that you don't have problems when you attempt the homework. The first function is not differentiable everywhere because the point of an absolute value graph is a point where the derivative doesn't exist. So instead of just saying we can't do this problem, what we do is we break it up into two different pieces. The left branch is certainly differentiable, and the right branch is certainly differentiable, and we can certainly find the area under this curve. We just need to separate it into two parts. If I pick numbers that are bigger than 3, the quantity inside the absolute value is positive, so the rules for absolute values just say rewrite this the exact same way you see it. If I pick numbers that are less than 3, 2, 1, or 0, the absolute value quantity is negative, so that means I need to write this with the opposite of what was inside there. I can't have a negative output from an absolute value, so I need to say the opposite of that negative quantity will make it positive. So the left function is this, the right function is that. If you were to look at your pre-calc way of graphing this, take an absolute value function, move it right 3, flip it across the x-axis, and then move it up 3 units, you'll get this picture. And these two lines do match the functions that were written here. So once you come up with the correct functions, you're off to the races. If I want the area under the curve from 1 to 4, I'm going to separate it into two different functions, one of which goes from 1 to 3, and the other one that goes from 3 to 4, because 3 is the place of where the derivative doesn't exist. So now, first function is x, y equals x. Second function is 6 minus x, y equals 6 minus x. Antiderivatives, substitute values, pay very close attention to the subtractions and all your signs, and you wind up with 6.5. For this one, you could actually figure out and confirm with geometry by shading this. And if you were to count boxes, you would find out that that area is indeed 6.5 units. Got to be a little bit careful because the boxes, that is 1, base of 1 and height of 1. 1, 2, 3, 4, 5, and then 6, 1.5 more. Okay, last example is the same kind of an idea. We have an absolute value plot, x squared minus 4. Instead of it being, having a place where the derivative doesn't exist, this is a parabola that goes below the x-axis. So to get the absolute value of that function, we sketch the parabola, and then we reflect it off the x-axis. So any place where the function starts to go negative, we just reflect it up to the positive side and continue on there, okay? So x squared minus 4 is a parabola that's been dragged down 4 units. I went over 1 up 1, over 2 up 4, over 3 up 9 to get points in either directions. and then I flipped it or made a mirror image across the x-axis. The question asked us to find the antiderivative from 1 to 3. So on the area under the curve from here all the way up to here. So I need these areas. So what I need to do is, again, take my function apart and say, well, from 1 to 2 is one function, and from 2 to 3 is a different function. What are those functions? Well, they're written right here. From 1 to 2, I have the opposite of the parabola x squared minus 4. Okay, I need to flip that across the x-axis. So I put a negative on the outside. The opposite of x squared minus 4 is 4 minus x squared, which does make sense. But then from 2 to 3, I have what I'm looking at, x squared minus 4. So its function is x squared minus 4. I pick up those two functions and put them in the right spot. From 1 to 2, 4 minus x squared. From 2 to 3, x squared minus 4. Antiderivatives, substitute values, antiderivatives, substitute values. I ran out of space, but trust me, if you do all the calculations correctly, you wind up with 4. And again, you can check both of these by using your calculator using Math 9. Okay, that's it. That's all the notes for day 5. We're going to spend 4 days on the fundamental theorem of calculus. That's how important it is.